Welcome to week 4. So when I last left you, you were dealing with special data types, such as dates or factors, or most importantly, strings. And so we're going to start this week with a slightly more complicated programming concept that is called regular expressions. And these regular expressions are designed to make it easier to work with strings, or to do some special processing of strings. So let's take a look. So what a regular expression is it's a way of fuzzy matching text. That's how I think of it. You did a lot of work last week, including in your lab, with matching elements of text. And some of the things I asked you to do, such as finding words that are more than 4 letters long in song titles, these things probably took you a few steps. You probably had to use those stringer functions and search for many different things in order to get this to work. With regular expressions, those types of tasks are going to be shorter because you're going to be able to specify kind of a class of things that you want to match instead of some kind of exact word or exact character. Regular expressions are not specific to R. Every programming language that I've ever heard of has its own version of regular expressions. The rules and the syntax might be slightly different, so when you learn a new language, you sort of have to relearn which symbols behave in which way. They're usually fairly consistent and fairly similar, but there can be quirky little differences. The type of regular expressions that R uses are called extended regular expressions, so that's the official term for every language that uses this type. So you may see these exact approaches that I'll show you today in other programming languages. Another thing you may run into if you Google for help on today's work is you may encounter a package called Rebus. And Rebus it's a nice idea. It's designed to make regular expressions a little more readable in R. So instead of constructing them with fancy symbols like I'm about to show you, you kind of write them out like words. Some people like this. Personally, I find this to overcomplicate. I find this harder to read than just sort of getting used to regular expressions, after which you can figure out almost anything. So you are allowed to use Rebus and Rebus-style regular expressions. Certainly I won't tell you not to. But I don't particularly recommend it. I don't personally really like it, and it's not how I'm going to teach you today. But I do want you to be aware of this in case you Google for help, encounter something that looks like it's in R, looks like it's the context you're interested in, but that regular expression looks totally different from anything you saw in class. We're going to be using a lot of string R today, so I hope that you internalized it a little bit last week. I told you that this is my favorite R package, and this regular expression approach is why. So there are a lot of functions built into base R that do their work through regular expressions. They expect to get regular expressions, they do fuzzy matching. Some things that might look familiar to you, there's a function called gsub and grep, and there's a few others that are kind of in that similar vein. They have the G's in front of them. They're actually copied from the syntax in C, if you've ever programmed in C. And these ones do the same stuff as the string R package. Personally, though, I find them super unpredictable. I find it really difficult to tell what object structure you're going to get out of it. It really depends on what object structure you give into it and what type of regular expressions you give it, and some of that is really hard to track. So I love string R because it's specific about what you're doing, it's specific about the output types. You practiced this last week, and I use it all the time for text processing. It's really simplified my approach to text analysis. So let's see some examples here. So when you're writing a regular expression, you're basically just creating a string that gives R instructions about what other strings should match. And so we actually already did this last week when you searched for certain words within your code. So if we search for the string Kelly, right, that phrase Kelly is actually a regular expression. It's just that that doesn't have any of the fancy shortcuts that regular expressions have. It just has some letters, and letters will always match themselves. So you never have to worry about a letter behaving weirdly, or a number for that matter. But there are times where you want to say, I don't care which letter, just give me any letter at all. And that's where we're going to use some of these special characters which involve those brackets. I'm not just using those brackets kind of to visually group things on the slide. That whole orange bit, brackets A through Z, if you put that into a regular expression, what it's going to match is anything from A to Z, any capital letter. And as you might predict, the same thing with lowercase letters matches lowercase letters, or you could go from capital A all the way down to lowercase z, and that matches any letter at all. There's also another shortcut that's the bracket alpha. Those are equivalent, whichever you like better is fine. Similarly, for numbers, we can go 0 to 9, and that matches any of those numbers, or we can use that digit shortcut. And I'll refer refer you to the StringR cheat sheet. I'll ask you to look at it a little later in this lecture. There's a lot more shortcuts. For example, punct matches, as you might expect, punctuation. And there's a few more for common classes of characters that we look for using regular expressions. So enough overhead, let me show you it. So here I have a string, Kelly, Jelly Belly, Smelly, and then I've got this 9 Ellie and Ellie by itself. And so if I say extract from this string, or from this vector of strings, all the instances of the word Kelly, of course it's only going to find it in that first element, so it's extracted Kelly, and the other elements do not actually have that exact match. They don't have K-E-L-L-Y, although they're similar. So now I want to match more than one of those things. So maybe I want to match anything that rhymes with Kelly, anything that's a letter and then E-L-L-Y. So I've got my alpha, E-L-L-Y. So now, using this function exactly the same, what I've given it looks like a regular expression. And this function actually knows to expect regular expressions in that argument. If you look at the documentation, the object type, or the data type that it wants, is not a string. It wants a regular expression, which is a different type of object. And so it knows to expect these sort of special characters, special symbols, and so it sees this and says, aha, what I should do is I should match any letter, and then exactly the letters E-L-L-Y. And so it did that. It got Kelly, K is any letter, Jelly, J is any letter, Belly. You'll notice that it got Melly, not Smelly. So there is something to do with number of characters here. This bracket thing is just a stand-in for a single character, whether it be a letter or a number or what have you. Something in brackets stands in for just one character. And then it didn't find 9 Ellie, because 9 is not a letter, and it didn't find E-L-L-Y because there wasn't that one in front, so that's not optional. We said, you must give me a letter that is followed by E-L-L-Y. Now, if we wanted that 9 Ellie, we remember we could have this digit shortcut that stands in for any number at all. 9 is any number at all, and so this extracts for us 9 Ellie, but none of the other ones. And so you might say to yourself, oh, well, how am I going to get Smelly, and how am I going to get Ellie? Am I going to match all of these things? And so you might have thought, well, Smelly, the problem there was it had 2 letters. The other problem is that people called me it all the time in elementary school. But our problem for coding is we have 2 letters, and we only asked it to match 1. So I could say here, give me a letter, any letter at all, capital or lowercase, and then give me a lowercase letter, any letter at all, and then E-L-L-Y. And so now we successfully got the whole word smelly extracted, but now it's no longer matching Kelly, Jelly, or Belly, right? Because Kelly, Jelly, or Belly don't match this pattern. They don't have 2 letters in front, they only have 1. So we're going to have to be a little fancier. We don't want to have to say, here's all these different things that might match. I have to tell R every single one that I want it to find. I would like to just use one call of this stir_extract function to match all the elements of this vector. So how we're going to do that is we're going to use some other special characters that R recognizes as part of a regular expression. So here are some of those special characters. Arguably the most important one is the period, the dot, because that matches any character at all. If you really don't care, you just want something to be there, then the dot will match that. The exception is actually new lines, like if you hit a return key, or a /n in some languages, that won't match the dot. So something that shows up on the next line of your text won't match any other character at all, it will match. But then we saw this problem where we wanted either one letter in front of Ellie, or maybe 2 letters in front of Ellie. So there's all these special characters that have to do with how many times that match is duplicated. So a question mark means I want the character preceding the question mark, but I want it to appear either 0 or 1 times. So basically it's optional if it's followed by a question mark. Or you can put a number in curly brackets, and that means I want that character to appear exactly this many times. So exactly twice in this example. Or you can kind of be vague. You can say it can be repeated so many times. And so you can use plus that says we have to have it. We have to have this character preceding the plus at least once. But it's okay if we have it way more than once. Or if it's optional, but you could have many, we have a star. It says the character preceding the star can happen 0 or infinity times. And so now we're making double use of these characters, right? You can imagine a string that has one of these special characters in it, and then you're trying to make a regular expression involving that string. And the way that we avoid problems there is that if we mean literally the character, I want to match a question mark, not use the question mark as a special command in my regular expression, then I have to escape it by putting slashes in front of it. So that was a lot. I'll show you some examples. There we go. So suppose I have this vector of strings, and I have varying numbers of L's in them. Key, Kelly, 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 Kelly. If I say, tell me which of these elements have exactly 2 L's before the Y. So I want KE, exactly LL, and then a Y. Of course, only one of them has that, right? Only the third one has those exactly 2 L's between the E and the Y. But now I could say, show me which elements of this vector have 1 or more L's. Remember that plus says it must be there. There must be at least 1 L, but we could have a whole bunch of them. And so we don't get key, right? Because key doesn't have that required L. But we do get all the other ones. We don't care how many L's there are as long as there's at least one. Or we could say that L is optional. I don't mind if you have lots of them. I don't mind if you have none of them. And now we've matched every element in that vector. We get key because it indeed has a K. I'll highlight that. It indeed has a K. Indeed has an E. It indeed has 0 to infinity L's, in this case 0. And it indeed has a Y. So we actually do match key here because I made that L optional. And we still match Kelly because I said many, many L's is just fine. Here's another example. So let's go back to that vector that had Kelly, Jelly, Belly, Smelly, 9 Ellie, and just plain Ellie. So now, instead of doing that thing where we separately said, give me a letter and ELLY, or give me a number and ELLY, now I can just use that dot and say any character at all, and then ELLY. And so now in one step, instead of in 2, I've combined matching Kelly, Jelly, Belly, Melly, and also 9 ELLY. Now notice there's still 2 issues here. One of them is that we aren't matching ELLY, because again, that dot is not optional. We can tell it to be optional using other special characters in conjunction with what I have, but the dot stands in for any character. There must be something there. We're just being vague about what that has to be. And we also notice that we're still getting that melly, not smelly. And that's the same reason. The dot is not vague. The dot says one character exactly right here, of any kind. So now if we wanted to get our smelly, we could say, before you had to put, I want a letter, and then I want a letter, and then I want ELLY. Now we're going to say, I want a letter exactly 2 times. I want exactly 2 letters, and then ELLY. And so now again, this gets us our smelly, but we still have that problem where Kelly doesn't have exactly 2 letters. It only has 1. So we haven't made this optional. We've said exactly 2 in front of the ELLY. But now we know how to be a little more vague, right? So now we can use this plus trick and say any letter at all, at least once, but could be many of them. So now we've gotten Kelly, Jelly, Belly, Smelly, and in the case of Smelly, we didn't drop the S because we said, well, you're allowed to have more than 1, and now we got the whole thing. But of course, now we've lost our 9 Ellie, and we still don't have our ELY because I said I've got to have at least 1 letter here. I used the plus, which says 1 or more of whatever comes before it. So then I could say any letter at all, 1 or more times. Now I get my 9. I've specified anything at all instead of a letter specifically. And so we've almost done what we wanted, right? We got all the elements except that last one because that last one has nothing in front of the Ellie. And I hope you've started to anticipate here how I might fix this. I still want any character at all, and I want it as many times as we want, but I also want it to be optional. 0 times is appropriate. ELLY has nothing in front of it. So now we can say I've got dot star, ELLY, and that says anything, any number of times, as long as it's followed by ELLY, we're golden. All right, one last example to do with these special characters. So here I've got another vector of strings. This one has some sentences. Kelly, hi Kelly, Kelly Budwin, and who is Kelly? And so I could say, please extract for me any instance of my name followed by a punctuation mark. And you get what you expect here. We have Kelly period and Kelly question mark period. Remember that those special characters, they're not special in the original strings. These are still just strings. They're only special if you use them in that regular expression instruction for where we should match these strings. So this works fine with that punctuation stand-in that says any punctuation mark you find. But then you might be tempted to say, well, I want just the one with the question mark. I don't want hi Kelly, I want Kelly question mark. And so you might be tempted to just put that into your pattern that you're trying to match, but this doesn't work. Because remember that the question mark means it's optional. It means give me the character preceding 0 or 1 times. So what we've really asked for here is we've said give me K-E-L-L and then optionally a Y. And so now it's giving me back Kelly, Kelly, Kelly. We find it in each of these strings because all of those contain K-E-L-L and 0 or 1 Ys. So if what we wanted instead of using that question mark as the special message of 0 or 1 of these, if we want the literal question mark, we have to escape it. We have to tell R, I want K-E-L-L-Y, and then literally give me a question mark. I'm not giving you special regular expressions here, buddy. Just give me that character, which is a question mark. And here we can see that gave me back what I wanted, just the Kelly with the question mark at the end. So that's the basics of regular expressions. You can do so many things. They're so powerful. If you just have this idea of the bracketing for matching anything at all, and these few special characters that I've given you. I want to give you some tips, though, because regular expressions can be tricky. My first tip here is read these regular expressions to yourself as though you're making a request, you're ordering at a restaurant. Read through them and translate those special characters into the words that you are asking for. So for example, here's a little quick quiz for you. Here's back to that vector that has the Kellys with different numbers of L's. What will this code return? Think about which function is being used. Think about what the regular expression is asking for. Here's how I would translate this into words. So the stir subset is not extracting matches, but rather it's figuring out which elements of the vector contain that match somewhere in them. So I'm asking which elements of this my stir vector contain somewhere whatever the regular expression asks for. What does it ask for here? Well, it asks for exactly 2 L's. I've set you a bit of a trap here. I think that probably most people watching this video said what this is going to give back is just the third element. Because this third element right here is the one that has exactly 2 L's. But notice the difference between this and the example I gave earlier. I didn't include the K or the E, and I didn't include the Y. So I said, look inside these elements and see if you can find 2 L's in a row. Well, this one doesn't have it, this one doesn't have it, clearly this one does, but this one also has 2 L's in a row somewhere in it, and this one also has exactly 2 L's in a row somewhere in it. And there we can see, indeed, it gave me back the last 3 elements of this vector, all the ones that contained somewhere 2 L's in a row. Let's do another real quick quiz here. So based on what you've learned so far, what does this particular combination of special characters match? The dot and then the star. You've seen it already, and I hope that this was fairly quick for you. If I translate this into English words as per the tip, I say, please give me any character at all. So the dot says I match everything. And how many of those do I want? Well, I want 0 to infinity, any number of any character. So what this dot star does is it matches everything. Every single string that you can give me is some number of some character, some number of times, right? It matches anything at all, any number of times. That's as vague, as generic as you can get. So my second tip with regular expressions is that it's always good to try a simple example first and try and break your regular expression. So always test these out on small examples first. And there's actually a really nice string R function for this, which is stir view, or you could also use stir view all. And if you run that stir view, unlike extract or match or detect, it's going to show you where in your text those matches appear. So here, I'll highlight it. I'm sorry it's showing up in white. We can see what was matched by the regular expression that I wrote. And now let me give you a final tip here. And that is, regular expressions are, forgive my French, a bitch. Everyone hates them, but everyone loves them, me too, because they are so powerful. The amount of things you can do with regular expressions is amazing. You can take a data set that is all kinds of wonky and transform it the way you want using just regular expressions. But they're so frustrating and they so appear not like English, and it is more difficult even than in ordinary coding to read through the regular expression like a computer and predict the output. So I do want to say, as you work on this is a topic that a lot of people find frustrating. Be kind to yourself. You are not the only one struggling with it. You are not doing it wrong because it is confusing and frustrating. Take your time. Be patient with yourself. Don't give yourself a hard time if you have to rewrite your regular expression many times. I do too. Here's a comic that perhaps supports what I'm saying. This is such a known entity, these regular expressions being frustrating to coders, is a meme. You can find all kinds of comics and memes on the internet about it. Here's just one. But like I said, they are so powerful. You can also find memes and comics about how great it is when your regular expression does work right and does do what you wanted. Because it's almost like being a superhero. Stand back, I know regular expressions. And now you do too, or at least at the end of this week you will.